This is the lecture to Module 1 of Unit 8, which provides an introduction to complex ion. The first module discusses complex formation. Complex ions are species which exist for the most part, in aqueous solution. They are typically formed from a cation, commonly transition metals such as chromium, copper, iron, and zinc. But it is also possible to observe complex ions made from aluminum in aqueous solution. Here is a typical complex ion in the picture, in which an iron cation is complexed or surrounded by 6 water molecules as an octahedral geometry. These are not actually bonds, as you will see, but electrostatic attractions between lone pairs on the water and the positively charged iron cation. Since the waters are neutral, the overall charge of this moiety is just the charge of the iron cation, which is positive 3. The species that attach themselves to the metal cation are referred to as ligands. Ligands are attracted to the metal cation by their lone pairs. Examples of ligands include ammonium, cyanide, hydroxide, and chloride. And, for example, the copper-ammonia complex, which has a positive 2 charge made from a copper and 4 ammonias. And another example is a zinc hydroxide complex made from 4 hydroxides, complex to a positive 2 zinc cation. Notice the overall charge of this species is negative 2, as it is produced from a zinc with a positive 2 charge and 4 hydroxides with a negative 1 charge. You should always make a note of the charge of the metals and the ligands within a complex ion. Coordination is the process in which complexes form from the attraction of the lone pair to the positive ion. For example, the formation of the copper-ammonia complex may be looked at as 4 reactions, or 4 processes, one after the other, in which ammonia molecules, attach themselves to the copper atom by attraction of the lone pairs to the positive charge. So the formation of this 4-ligand complex may be looked at as the result of 4 successive reactions, which result in the formation of the complex ion, which again has a net charge of positive 2. Naturally, the complex, this reaction of formation of the complex can be written as an equilibrium, is an equilibrium reaction. The equilibrium constant for the reaction has the complex in the numerator, and copper and ammonia to the 4th concentrations to the 4th power appear in the denominator. The equilibrium constant for this reaction and this equilibrium expression is often called the formation constant, K form, and it's typically very large. For this complex, it's 1.1 times 10 to the 13th, for example. Under this circumstances, with this large K, it is generally a reasonable assumption to make that this reaction proceeds all the way to the right. In other words, if you have copper and ammonia in the same solution, this reaction will occur until you run out of one or the other. Because K is so large, equilibrium problems involving these complexes are often addressed using the instability constant, which is the constant for the reverse reaction in which the complex breaks apart to form copper and ammonia. Naturally, the instability constant is the reciprocal of the formation constant and hence is very small. For example, let's look at an equilibrium problem in which we address the concentration of ammonia, free ammonia, in a 1 molar copper ammonia solution, which could be made from 1 mole of copper and 4 moles of ammonia, for example. Yeah, we assume that the reaction has gone to completion. In other words, our 1 mole of copper and 1 mole of ammonia and a liter of water completely form the copper-ammonia complex. Now consider the reverse reaction going on. The instability constant is 9.1 times 10 to the negative 14. And the equilibrium expression has copper and ammonia to the 4th power in the numerator and concentration of the complex in the denominator. We can regard the initial concentration of the complex as 1 and complex of the cation and the ligand free of the complex as 0 for a hypothetical initial state. Changes in concentration will be X and 4X for copper and free ammonia, while the concentration of the complex decreases by X until equilibrium is achieved. Equilibrium concentrations are then X, 4X, and 1 minus X for the 3 species. We will treat 1 minus X as 1 to solve for the concentrations. Alright, then that calculation gives, well, when we solve for X, 9.1 times 10 to the negative 14 is X times 4X to the 4th power over 1, or 256 times X to the 5th. Solving for that gives X is 8.1 times 10 to the negative 4. It's important for this problem to remember that that would be the copper concentration, whereas the ammonia concentration would then be 3.3 times 10 to the negative 3 molar. Not insignificant, it's true, but much less than the 4 molar that we started with before the complex was formed. A common problem or application of equilibria that you will see is using formation of a complex ion to increase solubility of an insoluble compound. For example, let's confine the solubility constant of copper hydroxide in an ammonia solution. KSP for copper hydroxide is 1 times 10 to the negative 14th under normal circumstances, and if we were just considering copper hydroxide and water, we would use this equilibrium constant to determine the molar solubility of copper hydroxide, giving us a very low molar solubility for this species. However, if we dissolve it in ammonia, remember that K for the formation of copper-ammonia complexes in water is very large, 1.1 times 10 to the 13th. Okay. We can view these two reactions as occurring successively. Copper hydroxide breaks into copper and 2 hydroxides in water. The equilibrium expression for this process is KSP is copper concentration times hydroxide ion concentration squared. Copper and 4 ammonias, in particular copper formed from the breakup of the hydroxide, can then react with 4 ammonias to form the copper ammonia complex. And the equilibrium expression for this process is copper ammonia complex over concentration of the copper times concentration of ammonia to the 4th power, as we have seen. Sum of these two reactions, A plus B, is the reaction of copper hydroxide with aqueous ammonia to make the copper ammonia complex and 2 hydroxides. And K for this, naturally, will be the product of the two reactions A KSA and B, or KSP, times K of formation. 1 times 10 to the negative 14 times 1 times 10 to the 13 is 0.11. And this will be equal to concentration of the complex times concentration of hydroxide squared over concentration of the ammonia. The solubility of the copper or of the copper hydroxide has been increased by a factor of 13 by addition of, by allowing the reaction with ammonia to occur. You can tell the formation of this complex in solution, by the way, because it has a very striking blue color. We'll talk more about the color of coordination complexes in the next module. A particularly stable variety of complexes is made with ligands with more than one donor atom. In other words, ligands with more than one site within the molecule with lone pairs available. Quote-unquote bidentate ligands, for example, have 2 lone pairs with which to complex a cation. For example, 1,2-diaminoethane or ethylene diamine. Structure of the molecule shown here naturally has lone pairs on both of the nitrogen atoms with which to complex or coordinate a metal. In other words, the ligand coordinates the metal at 2 sites. Again, this type of binding is very stable and hence K is very large for the formation of the species. Chelating, the process of binding with multidentate or polydentate ligands, forms very stable coordination complexes. An example of a hexadentate ligand, a ligand that forms very stable complexes, is EDTA, ethylene diamine tetracetic acid. A structure of this anion is shown down here. Note that 6 lone pairs are shown in red. There are 6 sites of coordination to a metal at EDTA, in the anion form shown here. Alright, this concludes the presentation for Module 1 of Unit 8.